for me, it's by far the most surprising part of this whole story. Because it sounds like it's going to be something very esoteric, right? Something that you really wouldn't care about. You have a quantum Hall fluid, and the basic point is that you have a quantum Hall fluid in a finite region of space, which of course you always do in experiments, then there's guaranteed to be certain modes that propagate around it. Okay, so that sounds fairly interesting. What's surprising is that these modes seem to know much more than they should about what's going on in the middle of the sample. In a way that kind of is similar in spirit, although not in details, to what happens in holography. So in holography, you gauge gravity duality, you have modes on the boundary, and rather amazingly, that knows all about the dynamics of gravity. Now, it's nothing quite as dramatic as that, because much less is happening in the bulk. But nonetheless, as we'll see, it knows about what's happening in the bulk in a way that's very striking and surprising, and if I'm honest, in a way that I don't really understand. So we're going to do the calculations and see how this works, but I'd love to get some better intuition on why this is working in adults, because it appears quite magical. Okay, so that's the plan for today and tomorrow, is to get to this point. Okay, so all of that is just to say the edge modes, these are more interesting than you might think. Okay, so let me just start by pointing out a very simple property which we can understand in a very simple manner. So the first property of these edge modes is that they're chiral. Okay, so what does chiral mean? The system is two-dimensional, the boundary is one-dimensional, and chiral means that the edge modes only move in one direction along the boundary. What's more, they're obliged to move, they're gapless modes. So they're in high energy physics we call them massless modes. In high energy physics we'd say they were obliged to move at the speed of light along the boundary. Here there's another velocity that plays the speed of light, and they're obliged to move at that speed. Move around the boundary. That's easy to see, at least the fact that they're chiral, even classically. So we can see this classically. And it just follows from a classical motion in a magnetic field. So this is the plane. Let's take the magnetic field to come out of the plane. We put a particle that moves in the plane. We give it a kick. What happens when it goes in a circle? But it can only go in a circle in a particular direction. In particular, if it's at the boundary and the circle, like that, so the circle, you start it at the boundary, you give it a kick, it comes back, it's going to hit the boundary, and then we have to ask what happens. Well, of course, it depends on what boundary conditions you put there. You could just be absorbed in the boundary, but if you want to sort of keep it in the game, the only thing to do is to give it reflecting boundary conditions. It'll come back out, and then it will do another little skip like this. And the upshot is that on one boundary, it skips along that way, and on the other boundary, it skips along going the other way. Okay, so even classically, you can see that if you have reflecting boundary conditions, you get these chiral modes. Okay, so for the integer quantum Hall effect, and I'm not going to explain how the integer quantum Hall effect works in this talk. It turns out it's very straightforward, and I did it in the very first section of chapter 2 of the notes, if you care. So for integer quantum Hall effect, it turns out you get a chiral fermion. For each filled Lambda level.
You can think of the edge mode as sort of skipping like that, is it?
Classic, that's right. If you do the quantum analysis and the integer quantum Hall effect, it's all just free fermions. You see that this intuition is basically chiral mode. They go in different directions, different edges. Okay, Okay, so I won't do this simple integer quantum Hall analysis here. Instead, I'll just look at the fractional quantum Hall effect. And here we get something much more interesting. And so the purpose of this lecture is to think about what we get on the edge for the fractional quantum Hall states and what their properties are. And so in this lecture, in fact, I think in both lectures, I'm only going to talk about the Lofton states. Maybe at the end of the next lecture, I'll talk about the non-abelian states, things like the Reed state, because they have some extra richness. Okay, I should say that everything I'm about to discuss in these two lectures was really first. The history is a little bit. At the end of the lectures, I'm going to discuss a result by Moore and Reed. That's kind of where this is going. In fact, all of the lectures that I've been given would get to this result.
Can I guess who might have done it first?
But who did this? Yeah, please guess.
Okay, either Halperin.
There's only 5 people who did it. No, it's actually one of the 5, but I've not mentioned it so far. It's Xiao Gang, who really initiated this study of these exploits in the way that I'll describe it. It's one of Xiao Gang's. He has a collection of papers. It's back when he was writing, for me at least, comprehensive. They're much easier with these things later. Okay, so there's a bunch of ways to think about these edge modes, in part because we've got a bunch of ways of thinking about the quantum Hall effect. So one thing you can do is just take the Lofton wave functions and just think about the excitations of the Lofton wave function. We've looked at some of those. We've looked at the quasi-Hall excitations. It turns out there's much simpler excitations that will describe these edge modes. You can just enumerate the edge mode and start to understand some of their properties. Okay? I'm not going to do that here. It's fairly straightforward. It's all in the notes if people are interested. Instead, the way to get the most information is to start with the Chern-Simons description. So to start with the effective theory of Chern-Simons theory in the bulk, and just think about Chern-Simons theory on a manifold with a boundary, and there'll be a whole bunch of subtleties that arise, and we're just going to figure out what those subtleties are and the way to think about this. So we're just thinking this lecture, and in fact, this whole lecture is really just going to be the story of abelian Chern-Simons theory on a manifold with a boundary. So Chern-Simons with a boundary, where the boundary is, of course, in boundary space. In the last week, we all learned where E and H bar go in Chern-Simons theory, so now just. So if you remember, in the last lecture, or the last 2 lectures, we looked at the Chern-Simons description for the Lofton state and filling fraction. U equals 1 over m, and it was just the Chern-Simons theory. There was an emergent U1 gauge field that I call little a. So it's not the same thing as electromagnetism, something that's dynamical. And the effective theory was and last week, of course, we understood the various properties of this and saw how it captures various properties of Lofton quantum Hall fluids. It has the right quasi-Hall, right statistics, right charge. So the new thing we're going to do is we'll consider this on a manifold with boundary. And ultimately, we're going to be interested in a little disk of quantum Hall field where the boundary is a circle. But in order to derive the properties of what's happening on the boundary, it'll be easiest to first think of the quantum Hall fluid as filling the lower half plane, so the boundary is a straight line. Just because it's easy to work with linear coordinates than periodic coordinates. So consider the boundary. So this is the Hall fluid, the Hall state. This is the vacuum. So the Chern-Simons theory lives in the lower half plane y less than 0. And then it stops here, and this action is to be thought of as just living in this shaded region. Okay, so what do we have? We have a classical action, and now it's defined on a manifold boundary. And there's two issues we're going to have to think about. The first issue happens for any classical theory when you have a boundary. And the second issue is specific to Chern-Simons theory, which is to do with gauging variables. So let me first think about just the basics of any classical theory when you have a boundary. Here's the issue. When you have a classical action, the thing you do with it, we learn when we're undergraduates, is you vary it to get the Euler-Lagrange equations of motion. Okay? Now, when you derive any Euler-Lagrange equations of motion, there's a part in the derivation where you integrate by parts and throw that away. And what's left, you say, has to be 0 in order to minimize the action. When you have a boundary in any classical theory, you can't throw away that term that you integrate by parts. And so if you want to minimize the action, you have to impose some extra conditions that guarantee that term vanishes. Those extra conditions are, of course, just the boundary conditions that you put. Okay? But the kind of boundary conditions you're allowed is hidden within this action through this variation. So let's just see what kind of boundary conditions we need to impose on the Chern-Simons.
Or you can have a surface part of the action.
So, of course, I could add a surface part that precisely implements those boundary conditions. Okay, so issue 1 is just what happens if we vary the classical action. So let's just see. We'll vary the Chern-Simons action. Vary the first gauge field, and then you get another term where you vary the second gauge field. The usual Euler-Lagrange is you want everything proportional to delta the field, not derivative, so we're going to integrate this by parts. If you integrate this by parts, you get two terms. This term picks up the extra piece with a minus sign, which gives the field strength. And the term that's left, which is a total derivative, is the following. This gives the equation of motion, which is just the field strength equals 0, but you only get the equation of motion from setting this equals to 0 if you can find a way to set this equals to 0. So, equation of motion, but only if this vanishes. Okay, so we need to find a way for this to vanish. That, roughly speaking, there are two possibilities. Either you set A to 0, or you set delta to 0. These are Neumann and Dirichlet boundary conditions. We're going to choose to set A to 0. But there's different combinations of A that you can set to 0, all of which will achieve the same thing. So we've got a bunch of options. We've got to decide which option we're going to take. So let me give you some examples. So one option is that we set the temporal component of A to 0 not down. Okay? That'll guarantee that this term vanishes. Another option is that we set the spatial component of A to 0 down. This will also guarantee that this term vanishes. The option we're going to choose, though, is a linear combination of both of these. So we're going to choose all of this equals 0. Okay. Now this linear combination has required us to introduce a new parameter v. This parameter has the dimensions of speed. Okay? And it's clear that we put this in by hand. This is going to be the speed at which the chiral modes propagate around the boundary. Okay? So if you think about this Chern-Simons theory itself, it's topological, it doesn't have any parameter of dimensions of speed. There's no way it can know what speed things propagate. So you're obliged to put it in by hand. It's extra information you need to tell the theory. This is how we're going to tell it, is by this choice.
But the same parameter will also appear if you use any of the other boundary conditions, right? Right? Because
the other boundary conditions come from taking the limit b equals 0 or b equals infinity. So it's really.
I'm saying, I mean, phi is something physically.
Yes.
I mean, it can be measured and so on.
That's right.
So it can't quite depend on what you're doing.
It's a physical choice. It's not a gauge choice. It's a physical choice of the boundary condition. Different boundary conditions correspond to different.
So how do I know in a given physical situation what is the phi?
You have to measure it and put it in by hand.
Okay, I see.
Yeah, the Chern-Simons theory alone doesn't contain that. It's something
I guess the point being made is that the boundary term will vanish as long as AT is proportional to AX, right? Because you have an anti-symmetrization.
Exactly. Yeah.
And so this is the most general way to express that.
I agree with you. It's a little surprising when you first
There seems to be so much of a choice. Right?
Yeah. So
This
I think is the most general choice. I think it comes with an extra parameter. The extra parameter has this physical consequence.
and it's also stated in terms of A, so which is not a gauge invariant
that's true.
way of.
That's true. Let me see. So if I do a gauge transformation here, it does.
But these are boundary values. Gauge transformation, which gauge transformation? Large gauge transformations.
Why independent gauge transformations? Let's say so they preserve the boundary.
No. We'll see in the next. We'll see shortly why those gauge. Why this is a gauge invariance. It's to do with issue 2. Issue 2.
That's about gauge invariance.
Yeah. Okay. Any more questions before I run this? So, issue 2, gauge invariance. All right. So this is an issue which is specific to Chern-Simons theories. And the point is something we've seen before, that if you do a gauge transformation on the gauge field, the Chern-Simons action is invariant only up to a total derivative. And previously we got to ignore that, but now we have a boundary, that total derivative is going to come back and bite us. So the Chern-Simons action sorry, it's a bit cramped on the end of the board there. The computer will read it. It says BTAX minus the X beta. So this is a problem because our action has to be gauge invariant, and now we find that it's not. So there's two different ways to fix this, which I think are basically ultimately the same, but people sort of talk in a slightly different language in the literature. So some places in the literature you'll read, well, this isn't gauge invariant, so we need to add to the boundary extra degrees of freedom, which are also not gauge invariant. And typically they're not gauge invariant in a subtle way to do with the anomaly. So you add anomalous degrees of freedom where the anomaly cancels this, and then the whole action is gauge invariant. Okay, that's one standard way to do it. I don't want to do that approach here because I'll have to explain about anomalies in case people haven't seen them or forgotten them. So we're going to do a slightly different approach, which ultimately will lead to the same conclusion. What we're going to do is just limit the gauge transformations that we can take. So we're going to choose to work with gauge transformations. A omega at y equals 0 matches.
Small gauge transformation.
If you like, usually large gauge transformations is to do with what's going on in infinity.
Yeah.
But yeah, the analog of that with a boundary. I'll insist that the theory only has gauge symmetries with this. You can see that obviously, if I restrict to such gauge transformations, Chern-Simons is now gauge invariant. Also, the alternative has the happy consequence that my boundary condition is also gauge invariant. Okay. All right. So that sounds a bit too quick, right? I just say, it doesn't look gauge invariant. I'll just look at smaller class of gauge transformations. But there's a consequence to doing this. Okay. So what's the consequence? Gauge transformations in any theory relate two different field configurations and state that these are physically equivalent. In other words, you have what you think are degrees of freedom, and gauge transformations kill those degrees of freedom by the quotient action, by relating them to other things. Okay? It's the usual statement that gauge symmetry is a redundancy in your description of the system. So now I've got a theory that has a smaller class of gauge transformations, which means that some of those field configurations that previously were related by gauge transformations and therefore unphysical are going to become physical because I'm no longer imposing that set of gauge symmetry. So by restricting the class of gauge transformations I'm doing, I'm bringing back from the dead some of these degrees of freedom that I previously killed. Those degrees of freedom are precisely going to be the things that live on the edge, which, if you'd gone through the anomaly route, would have cancelled this through. So that's the calculation I want to do, is to show to you, if you restrict your gauge transformations to this, you'll find that there are new degrees of freedom which live on the edge. So this is...
Sorry, because I don't want to interrupt this flow, but had you thought in the old way of putting extra degrees of freedom, whose anomalies would cancel, then those degrees of freedom would also enter here, I think, because if they lived on the boundary and they coupled with the gauge field, you would have a mu, j mu, and this would sort of set some analog this. Anyway, it sort of works out, I think, but that might be a...
This wasn't an equation of motion, this was just a boundary condition, so maybe I could still get away with this. It depends on whether... Probably I'm okay, because if it was delta A mu, then this is already of the form you don't have to integrate by parts. So probably it doesn't affect the boundary condition. But of course it affects the equation of motion.
You should go in, but this A mu, J mu would be on the boundary itself.
Yes, exactly. Yeah.
And then, so you get on the boundary delta A mu, J mu, and the extra term down, which is, this epsilon, this A mu, delta A.
Oh, I see. Sorry, that's on the boundary. Yeah, you're right.
And then the two will...
Yeah. Okay, so nice on the there.
Okay.
So doing it this way, we restrict to the gauge transformations, and this brings u degrees of freedom. Precisely those degrees of freedom would have been killed had we had more general gauge transformations. So let's see what they are. I think I screwed up a minus sign. My bad. Sorry, I want to do that. I want to set b to minus. Okay, so what's the plan? The plan always in Chern-Simons theory is you pick a gauge and then you look at the equation of motion in that gauge, where the equation of motion is now sort of a constraint. Typically you pick A0 equals 0, the equation of motion F12 equals 0. So here, because we've already got the boundary condition to be this, the sensible gauge in the bog is also this. Okay. So we're going to pick AT minus BAX equals 0 as the bulk gauge fixing condition. Okay, so we extend this all the way to the bulk, but now it's a gauge fixing condition rather than the boundary condition. Of course, it's nice that it also includes the boundary condition. All right, this is a slightly awkward gauge fixing condition to work with. So there's a trivial way to make it simple. We'll just do a coordinate change of coordinates. So define my prime coordinates like this. How do the gauge fields transform? They transform like this.
This is like the plane of the edge current itself. It's a
Exactly.
plane.
Yeah, exactly. Yeah, that's a good way to think about it. So the
If it were, sorry, relativistic, it would be the light cone.
would be the line code. Yeah. So the gauge fixing is now very simple. It's just A prime T prime equal to 0. So the constraint, which is basically Gauss's law, is the equation of motion for A prime, is F x prime y prime equals 0. And we know how to solve this. It just says that the AI has to equal gauge. So it looks like we've not found anything new here. We've solved the bulk dynamics and we found that it has to be pure gauge. But if you think about it, that's exactly what we wanted. The fact that we've got this restricted class of gauge transformations means that some of the things that were previously pure gauge have now come to life and are now physical degrees of freedom. So this should have been what we got if we did this. So what we're going to now see is that phi comes to life, but it only comes to life on the boundary. So phi becomes dynamical when it's on the boundary. And we're going to see this by plugging this into the original Chern-Simons action and just see. So plate is phi becomes physical on the boundary. Okay, so how do we see it? We plug into the action, and in AT prime equals 0 gauge, the action is I. So this is in the gauge AT prime equals 0. There's the extra term was AT prime F12, but that vanishes by the constraint. So I'll plug this into here. X prime phi, T prime, Y prime phi. That's what I get. You can see that it should be a total derivative in I. Oh yeah, it's a total derivative in y. To see that, I'll have to integrate my parts in x. There's no boundaries in x, so I'm going to have to do that. You can see that it's a total derivative in y, which means that if I write a total derivative term, which means it becomes a boundary term. So I get this, and finally, if I write it back in terms of my original coordinates, it becomes the following slightly weird action. Okay, so this is the price you pay. You have Chern-Simons theory with a boundary. In order to keep the gauge invariance, you're obliged to have bosonic field phi, which lives on the boundary, has the following very weird action. Okay. This has a name. It's called the Florianini-Jacobi action. Okay, any questions? Good, so, okay, it's a slightly on action. Well, one of the reasons it's on is that it's actually Lorentz invariant, even though it doesn't look Lorentz invariant. So it's one of these actions where you've given up the symmetry when to write it, even though the equations of motion have that symmetry. So let's just see what the equations of motion are, because the action's weird, but the equations of motion are dead easy. So the equation of motion is dt minus x phi minus b dx squared phi is 0. And we define something I'll call a rho, which is d phi by dx. I'll show you why there's a factor of 1 over 2 pi short. It's useful to have that there. And rho obeys the following equation of motion. No, that would be rho 0, rho 1. So it's a continuity equation, but where the charge is proportional to the current.
Yeah.
But that's actually the right physics. So this is the equation for a chiral boson. Okay, well, why is that? The solution is any function which is of the form rho of x plus bt. Okay? In the sense that it's any profile of rho where it travels with speed of v in that direction, but not rho x minus bt.
So one question, given the direction of the magnetic field and the boundary, the chirality must be fixed. Right now, the way you did, do I have replaced v by minus v? Or?
Good. You'll only see the problem when you come to write down the Hamiltonian system. And the Hamiltonian will be proportional to v, and it will be unbounded if v takes the long side. So that's where it goes. Okay. So I should say, just in general, there's a well-known difficulty in writing down actions for essentially chiral bosons. Okay, so what does that mean? In 2 dimensions, it means the difficulty in writing down an action for a boson that can only travel left. In 4 dimensions, the analog is writing down an action for a self-dual gauge field. And there's analogous things in higher dimensions. In type 2b supergravity, the difficulty is writing down the action for type 2b supergravity because it includes a self-dual phi field. Okay, so there's a sort of long story about doing that. In 1 plus 1 dimensions, there's various ways people have tried to do it. The Florianini-Jacobi action that I had here is perhaps the most successful, but it does have difficulties. And the difficulty is to do with the 0 of phi. What happens with phi being constant? So I'm just going to brush these difficulties onto the carpet here, but none of these approaches to writing down actions is quite good.
Sorry, this is a good question. But what if we don't keep v constant?
That's not a good gauge flexibility. Yeah, will v depend on x and t?
Yeah.
I think that's not a big change. That would be my initial guess.
There's a delta A in that. In that case, there will be delta B. Will be varies on the boundary.
No, it's because the boundary condition was, let me see, d mu, it's all mu rho, a mu, delta a rho. So you want to set evaluated at y. This is the same as saying evaluated at y equals 0. So epsilon y mu rho, y equals 0. You want to set a mu, so at minus b of x comma t ax. Let's just do that. So does that work? Yeah, it seems to be okay, right?
But then delta AT will not be proportional to delta AX. Right? I mean, there is a nu delta A rho.
No, delta doesn't change this. Delta just changes field. Do you know, I think what's going on here is the following. The Chern-Simons theory is completely topological. It doesn't know about any background metric. The only place a metric's going to appear is in these boundary conditions. And I think that doing this is analogous to changing the posing a different choice of metric on the boundary. That's what it smells like to me, at least. So I think you may have a larger, more options. We're just going to take the simplest case. Okay. We didn't miss much. Just that this is the action for a chiral boson where you write it in terms of the derivative problem. Okay? Any questions? So this is the new degree of freedom on the boundary. It's a left-moving boson. Had you, by the way, just another aside for those of you who know about anomalies, you might have been tempted to add a left-moving fermion on the boundary because that's the usual thing that has an anomaly. They're related by bosonization, and we'll see explicitly how they're related. Okay, let me tell you one further key point, which actually is important for the bosonization story. We'll see later. The key point is this guy here is actually a periodic vector. So this will be crucial when we think about the kind of operators we can write down with phi in. So why is it a periodic variable? It's because this kind of it arose as a pure gauge for a mu, but this is shorthand for a mu equals I e to the minus 1 d mu g, with g being e to the I phi. So I get my minus and right. Okay, usually we only need to write this for non-abelian gauge transformations, but of course it's also true for abelian gauge transformations. The reason it's worth stressing that is because phi in a gauge transformation sits in the exponent. So phi is periodic in period.
Sorry, can I ask you? Are we saying that can Chern-Simons theory be defined for a non-compact number?
It can be, and then phi is not periodic. But we made a big deal about it being compact because that's precisely what gives us the quantization condition for n.
I guess the difference is whether you have monopoles or not.
Exactly, that's exactly the difference.
Right now, of course, your boundary is a real line.
Yes.
Periodicity is not coming into the picture.
You're a step ahead of me. That's right. We'll get there. Okay, so what does this mean? It means that phi has period 2π. And it's what's called compact chiral boson. I want to just give a side note for people who know a lot about conformal field theory. I should say, in this lecture and the next lecture, everything I'm doing is really sort of in conformal field theory, but I'm not going to use that language because I don't want to assume that the people have studied CFT. But if you have studied CFT, a lot of this is going to be familiar, so I just want to make a few side comments for those that know about this. So in CFT, so we have something called compact bosons in CFT, and there's a slight normalization issue. So in CFT, you would usually scale phi goes to the square root of m phi. Okay, why is that? It's because the action is quadratic in phi, and at the front of the action is an m over 4 pi. But in CFT, you usually have the action being sort of canonically normalized. So when you would usually rescale this, so the phi has canonical kinetic term. Well, at least it's canonical as you get in this weird really intuitive action. And then the periodicity is 2 pi over the square root of m. Okay, so I'm not going to use this rescaling in these lectures. I'm going to keep phi to be periodicity 2 pi and have the m outside the action. But if you know about conformal field theory and you want to translate into periodic compact bosons, this is the radius of the boson you should need. Okay, any questions about this? All right. Okay, so we've got this boundary, and we've got this boson that lives on the edge, and it would be nice to understand how that boson is related to stuff in the real world, because this is actually something in an experiment, and in particular where the electrons fit in. So we're going to do a lot of this, understanding how electrons fit in, and so on. But let's just think about it classically now, and then in the rest of this lecture and in the next lecture we'll see quantum mechanically how we should think about electrons, because the whole story is related.
So first, one very small question. So usually a compact boson just writes, as you said, the canonical relativistic action, right?
No, you usually...
maybe if it's chiral, that's not true.
Yeah, that's the whole issue. Yeah. It's true, though, that this phi, you could just think of as the left moving part of it, massless. The propagator is the same.
So this unconventional action sort of ensures
it gives you the right propagator. And I think, in the end of this lecture or the next lecture, I'm going to talk about propagators. But it's very hard to derive it from that weird action. There's some horrible contour integral, so I'm not actually going to do it. I'm just going to tell you the answer. It's the usual log.
But if that is true, then of course fermionization is easy. I mean, it's just Coleman-Mandelstam, so you can get electrons through the fermionization of that chiral boson. But that's presumably not how you're going to get.
No, that's exactly how. It's the usual bosonizations.
That's exactly what I was also asking. If you could map it there, then
yeah. Okay, so this is sort of building up to this story. The first thing to say is that rho, which if you remember is 1 over 2 pi by dx. So this is the electric charge on the belt. Okay. And in particular, this 1 over 2 pi is needed so that it's precisely the electric charge. So rho is a function of x and t along the boundary, and it's telling you the excess or the deficit in electric charge position x. So let's see how, let's just show why this is true. So to see it, we need to remember how the Chern-Simons theory couples to electromagnetism. So the coupling is, remember it's always in any theory. So capital A is now the background electromagnetic field, and J is the current to which it coupled. The only dynamical degrees of freedom we have in the effective field theory is little a, and there's only one way to make a current out of a conserved object, and that's to write 1 over 2 pi Px. Epsilon mu rho capital A mu. Okay, so this is something we discussed last week about how you couple the effective Chern-Simons theory to a background electromagnetism. All right. Now we have a problem. This can't possibly be right. And the reason is that this is not invariant under gauge transformations. Now gauge transformations are capital A. So what did we do previously? Previously we said, that's all right, let's just restrict to gauge transformations which vanish on the boundary. But for real-world electromagnetism, I don't get to do that. That's not under my control, right? Because electromagnetism is still existing on the boundary and beyond the boundary. Little a was different. Little a only went up to the boundary and stopped. There was some emergent degree of freedom due to electrons. So you can imagine you're allowed to restrict gauge transformations there, but I can't restrict gauge transformations for real-world A. That's not part of the game. So somehow this isn't right. This is not invariant. A mu is A mu plus d mu lambda. And this is just not acceptable. So the answer in this case is not to play some silly game and try to resurrect this. The answer is just that this is wrong. This is not the correct way to couple electromagnetism. Okay? But it's very close to being right. So the right answer is that you integrate by parts to move this over here. There's a boundary term, and you just get rid of the boundary term. Okay? So the right answer is a different action, but it's an action which is gauge invariant. It's gauge invariant under gauge transformations of electromagnetism, but not under gauge transformations of little a. But that's okay because we've restricted gauge transformations of little a's. So instead, integrate by parts. And discard the boundaries. So the right way to couple electromagnetism is this way. In particular, all of the results we derived previously about coupling to electromagnetism hold equally well for this action and this action, because they only differ if you have boundaries.
So let's see, so the boundary term would be epsilon mu mu, capital A mu, small a mu.
Yeah.
And you're saying that your boundary condition on small a mu already ensures that this term is zero?
No, the term is not zero. There's a boundary term, and it's what makes this an illegal action. So we just throw it away by hand. And this is the correct action. So said another way, this...
What's the physics of throwing that away by hand?
There's no physics. The physics is that this is wrong and this is right. So the two differ by a boundary term.
I see.
This is the wrong choice.
But will we still be able to do this because they're equivalent if there is no boundary? The different way. Question.
Do you have questions? Okay. So this is the right action. All right. So now we can see how it couples to electromagnetism. And what we do is we plug in our live degrees of freedom, meaning we put A mu as d mu phi, and then we see how phi couples to the background gauge field. And in doing that, we're going to understand the interpretation of phi as it comes to electromagnetic background field. And so plug in classical solution. remember, well, A is something which is under our control, so the calculation is much easier to interpret if we set y to be 0 and the background fields to be to not vary in the direction perpendicular to the vector. Just make life a bit easier for us. And then what do we have? It's going to be simplest to go back to these private variables, and then we'll do the map back. So
why did we say d by at equal to d by, that's just the background which
I get to choose, exactly. We'll see the step where we throw it away. And so there'll be extra terms that come. We didn't do this, and we must have an interpretation, but not so straightforward. Okay, so having set this and this gives this. This, of course, is that. And now, because this doesn't depend on y, this is a total derivative. So it just gives us a boundary term. Okay, we get two terms. Okay, the first term doesn't contribute. So if we integrate by parts, this gives me t prime phi. But if we evaluate this on the equation of motion, then phi is a constant. So let me say this more clearly. On the equation of motion, rho, remember, was the left-moving object. Okay? Which means that in terms of t prime, dt prime rho is 0.
So we are varying this now with respect to phi.
No, I'm not varying with respect to phi. I'm just I'm taking the classical action and I'm evaluating it on the particular background field phi to get the interpretation of how phi is coupling to a background field.
Okay. And which particular phi, the one is the one which satisfies this equation of motion?
Good. So at the moment, phi up to here, phi hasn't. It's just been general. But now I'm going to take t prime rho equals 0. That's the equation of motion for rho, which means that t prime phi is just a constant, which means that this term is independent. And it's just this term I'm going to be left with.
So wasn't rho dx of phi?
Exactly. Okay. That's why the constants come from the integration. Okay, so we'll ignore the first term. And the second term gives us 2.5. Gives us this. So what have I done? I integrated by parts, put the x prime on this. X prime is the same thing. Same thing.
X prime. No, x prime is the extra.
Yeah, and then somehow that extra term there is disappeared.
T prime and X prime was there.
The X was X.
X was, no, I think X was,
Well, at least T prime first.
yeah,
T prime is T and X prime.
there's a flip. X prime is the interesting thing, but A of T prime is the interesting thing. They get flipped with this action. I see, sorry, there's some algebraic issue here which I'm not going to be able to resolve. Let me tell you the upshot and then I can. So the upshot is that AT couples to dx5 with a 1 over 2 pi, which is, of course, AT couples to the electric charge. Meanwhile, AX couples to the current. The current is just minus V times the electric charge. But that, of course, is what you expect because rho is a chirally moving object. So if you have electric charge here, it's got to be moving with speed of V. So, of course, this is the current. Okay? So this is the right interpretation. And I seem to have screwed up here. And it may have been that this argument was a bit too quick as well. Sorry, it is T prime is the same thing as T. Okay, so that goes there, and this is not the equation of motion. The equation of motion is the bit you get from this, and the other bit you get from this. Oh, but these differ too. I think that's true. I think if you do go to the other variables and then you integrate, you'll find that some of the terms vanish. The term that's left is this. I leave that as an exercise. I got very puzzled when I was going through this calculation. But it did work out in the end. I'm annoyed that I didn't write in my notes how it worked out. Yeah, sorry, no, it's written wrong in the notes. I'll try and fix it up in the notes. This is what I got. All right. Okay, so is this okay? Up to the things I screwed up.
So minus V goes the cut.
It's whatever way it goes. Yeah, minus signs are up to a minus signs are correct. Up to a minus. All right. There's a beautiful consequence. It's really, I think.
So why do we only need to? We have all of this only on the classical solution, right?
No, we're going to do quantum next.
Oh,
It's just easier to. All right. So let's look at a lovely consequence of this. We'll do. Galton was ahead of the game here. He suggested we should think about doing it on a circle. So let's consider Chern-Simons on the disk. So this is where the Chern-Simons thing is. And there's a periodic coordinate, spatial coordinate neighboring the boundary, which I'm going to call sigma. And it varies from 0 to L. So L is the covariance of the boundary. And let's look at the electric charge which lives on the boundary. So the electric charge is now Q is 1 over 2 pi times the integral of the sigma equal to L of rho. Sorry, no 1 over 2 pi, just the integral of the electric charge. Which is 1 over 2 pi, the integral of 0 to L of sigma pi by sigma. Which is a total derivative. So you might think it vanishes, except phi is periodic. Which means that as we go once around here, possible for phi to wind once around its periodicity. In other words, this is equal to some integer n, where n is the winding what's lovely about this is Q is the genuine electric charge in the real world that lives on the edge. It's carried by, normalized in such a way that it should be integer valued for electrons. Okay? And what we're seeing is that the electrons on the edge here have their representation as basically solitonic objects in this field. Okay? Because they're objects where the value of phi has to wind past. What's more, electric charge, real electric charge in the real world, isn't quantized in the way we usually think of because of quantization. It's quantized for topological reasons in this set. So the electron is a solid. It's very, very simple solid, but it's a soliton. Someone who spent a long, long time working with solitons, it's just really nice to see it emerging in a real world situation, just in a very easy way, but actually to be the electron. All right, any questions? Good. Okay, so far it's all been classical. And the next thing to do is to start thinking about quantization of this system. So what I want to do now is
which field is the electron? Sorry, which field is the electron?
Well, the electron is not so much a field. The electron is, every time phi winds once, as you go around here, there's one electron sitting there. Okay. We'll see next how you write down the quantum field for the electron. That's really where we're going. But just in this classical picture, the electron is a solid. It's winding.
So instead of getting rid of that omega degree of that gauge parameter at the boundary completely, you could have left some constant value of the omega or not, because
no, I think that
eventually rho only the zero mode of phi will probably see that, which we don't care about. Rho will not see that.
The zero mode of phi is very subtle in this game. And you're supposed to treat it
that
properly.
will jump. I see. So this is. I see.
You're supposed to treat it properly, and there will be a place later where, in fact, you know the place. It's when all the calculations we're going to do coming up are exactly the same calculations you do in the first course in string scattering. Exactly the same. And if you remember when you compute scattering amplitudes of vertex operators,
I have to integrate out of zero mode to get the momentum conversion.
And that's going to play an important role here as well. And so we're going to kludge it. We're not going to do it properly. But, you've done it properly already. You did string theory.
Yes.
Yeah, the zero mode is important. Okay. Any questions? So the next step is just to quantize this. It's just going to be basic quantum field theory. We're going to just write down the fields, write down the action, think about Fourier modes, write down command for quantization, just everything straightforward, and then there'll be some beautiful things that emerge just from it. So quantization. So the action we want to quantize. I'm going to put it on the spatial circle. It's this slightly weird Fourier-Nini-Jacob action. It's quadratic, so it's a free action. We'll just go ahead and quantize it. One of the weird things is that it's first order in time derivatives, which means that the momentum conjugate to phi is the thing we've called rho. Now, if you go ahead and just naively quantize, you get a factor of 2. It's kind of annoying, and I think it's to do with figuring out properly what a conjugate pairing in this language. So the way to do it carefully is just to go to Fourier modes, which is very natural. Quantize using Fourier modes, then it's just quantum mechanics, and there's no confusion. I'll point out where the factor of 2 arises in that case, and then we'll go back to the continuum. Okay, so we're going to take a slight diversion.
Actually, that factor of 2 can be understood as the difference between Dirac bracket and Poisson bracket. Because there's a constraint in the system.
Oh, it is a really easy
Yeah,
concept.
yeah.
I didn't know.
What's the constraint here?
It took me ages to figure out because there's several textbooks I won't mention that just do it wrongly with the wrong factor of 2. And it's particularly annoying because the same textbooks elsewhere do it using Fourier modes with the right one. And never comment. Okay, so we're working Fourier modes.
Now we're going to know which textbooks these are.
Show the authors. It's a great textbook for the content, for the stuff it covers. And it's a rubbish textbook for the way it explains the stuff it covers. So, you should buy the textbook just for the table of contents at the beginning. That's brilliant. But then the actual explanations I'll tell you when it comes. It's a Fourier transform of a good textbook because everything's in there neatly in the wrong place. So the quantization. In sigma from L and okay, so the usual thing, we take Fourier modes and phi minus n is the complex conjugate of phi n because phi is real. So to plug this back into the action, there's one line that I've skipped. One line of algebra that I've skipped. But it might just be possible to do it in the way. This is the answer. Okay, you can roughly see every time there's a phi prime, it pulls down a factor of k subscript n, where this is the momentum. There's actually a k minus n and a k minus n here. But of course, that's just minus k, so that's this minus sign here. And the final point, which is this subtle factor of 2, is that there was a 1 over 4 pi, but I want a 1 over 2 pi because I'm only summing over modes n greater than 0. That's the factor of 2 you miss if you do things naively.
Yeah, so that's the constraint on the initially balanced surface because not all phi n's are allowed by this. Only half of the phi n's.
Yeah, only half are independent.
Yeah.
Right, I get to specify just the phi n's greater than 0, and the others are the conjugate points.
Yeah, so that's the phase-based constraint.
Exactly.
Is it the old complex variables versus real fields? Like if you take, usually you integrate, we get this sort of things, not in this form, but in somewhere when you do expansions around superconductivity and so on. And then if you want to write it in actual phase fields and antecedent fields, which is the real fields, then you often get a factor of half. Again, comes from something like this, that phi minus n is phi n star, and they're not independent objects.
Yeah, it's not so much just that as the restriction to the innovative thing.
All in and allowed for each of the other categories. They need twice.
All in and allowed.
Okay, so what are the degrees of freedom? If you think about Q's and P's in classical mechanics, it's clear that this is of the form Q dot times P, where Q dots are the n's greater, where Q's are the n's greater than 0, and they're conjugate momentum. Minus n. which means that if you quantize, you get n by prime is 2 pi m 1 over kn delta n minus n. But by the way, I should be clear that if we take these to be the coordinates, the conjugate momenta are proportional to phi minus n. But there's a whole bunch of extra stuff. It's this, and so that extra stuff I put on the right hand side of the commutation relation. Okay. Meanwhile, we can also write down the commutation relations for the Fourier modes of the charge density. Charge density is rho n. So charge density is 1 over 2 pi defined by x, which means that the Fourier modes are pi n over 2 pi I, which means that the commutation relations are rho n pi minus pi n prime. Rho n over pi. The commutation relations are these. If you want some fancy words, this last one is called the U1 Kac-Moody algebra. Okay? Well, why is that? It's basically because K is proportional to A. Right? So it's U1 Kac-Moody is not quite as interesting as non-abelian Kac-Moody algebras, but this is what we've got here. It's a U1 Kac-Moody. So finally, we can go from here. We can go from Fourier space back to real space, and in real space, equal time commutation relations. Which you get from these Fourier modes. Okay, so this is this is the basic quantization. Any questions?
As you were saying, what we normally do in CFT is go to the holomorphic coordinates and write logs, and I guess this is what log becomes a sine and a delta.
Yeah, so
if we did it in sort of carefully in terms of the standard quantization.
propagator is going. These are going to be logs.
Yeah. I mean, I've actually not thought about compact boson in this language.
Yeah, it's
sine and all. The log is a very natural thing in 2D.
exactly, and we will get to that.
It's nice to.
Okay, so I'm just wondering. Are people happy for me to go on just for 10 minutes or is,
Yeah.
yeah? let me do that, and then it means that I can finish a little bit earlier tomorrow, and we can have some time to discuss it. Quite nice. Not least because we're going to end on the result, which is, like, as I mentioned earlier, it's quite baffling to me, so it'd be nice to have some discussion.
This is tomorrow, the last lecture.
Tomorrow going to be the last lecture, yes. Shiraz actually wanted a summary lecture, the very last week of the lecture. So maybe we can do that if this happens. Alright, so the last thing I want to do today is just revisit this question about how we start to see the real objects in the game, how we start to see electrons. So we saw classically the electrons come from 5 windings you go around the edge, so some kind of solid. So the question is, what's the quantum mechanical motion? So the claim is the quantum operator for an electron is operator psi, which is the normal ordered e to the I n phi, where normal ordering means all the phi to the minus n's, which are the annihilation operators, moved to the right. Okay. Notice that the phi is periodic in 2 pi in my conventions, which means that I can put it in the exponent, but only if what's here is an integer. And of course, m is an integer because it came from the Chern-Simons level and it was quantized to an integer. Alright, so let's just see if this is a sensible statement. So I claim that this is an electron. What can I do? I can check if it has the properties of an electron. So I can check if it has the right charge, and I can check if it has the right statistics, which means that it's got to be a fermion in our world. Now, the last part is very surprising because phi is a boson. So if this is to make any sense at all, this has to be a fermion, even though this is a boson. So that sounds odd, but we'll see that that is indeed the case. Okay, so let's now prove that this has charge 1 and is a fermion. By the way, for those that know, this is the main formula of polarization, fermionization. Okay, so let's check. So firstly, the charge. Well, how do we figure out the charge? We take a state, we hit it with a creation operator by dagger. We then measure the charge before and after we do that, which means that we have to, the charge should differ by 1, which means that we want to compute the commutator of the charge operator rho with the electron. Okay, it's very easy to do because we use the thing I just dropped off. We use this commutation relation. So what can you do? You can expand out this and take the commutators, put it back together again. You get this. So this means that it inserts of charge. Okay, and I should confess I'm not being careful about minus signs, whether this is a hole or an electron operator. If it's wrong, just put a minus sign. That's charge modulus 1. That's the statement that it's So check 2 is that phi is a boson. Psi should be a fermion. does this work where we use the VCH formula, you can handle L-swap, and you just write phi of sigma psi of sigma prime. And VCH says that I can write this as minus m squared times the commutator. You need to play around with VCH once or twice just to see if this is a good way of writing it. So if I flip the order of these, I get the same thing by the Baker-Campbell-Hausdorff formula up to the following expression. And remember, these commutation relations equal to this. If I remember correctly, which sign doesn't matter. Because it can be sign plus or sign minus, but I get I, the m cancels one of those m's, so I get I pi times integer. Plus or minus that, but that's the same. So what I find is that if sigma is not equal to sigma prime, so these are spacing separated, then psi commutes if m is even, which means that it's a bosonic operator if m is even, but it anti-commutes if m is odd. Now, this is the first sign that something deep is going on here. Because if you remember, when we talked about Laughlin states, we wrote down Laughlin wave functions, and there were functions zi minus zj to the power n. They were anti-symmetric when n was odd, they were symmetric when n was even. So these were states that describe quantum Hall fluids for bosons when n is even, and for fermions when n is odd. Now, when we got to the Chern-Simons theory, all we could tell was that n was an integer, because we didn't have any way to put in the information about whether they were bosons or fermions. It was sort of a much more coarse-grained description. But now we've got to the edge, we can actually start to see that the Chern-Simons theory did know about whether these things were bosons or fermions after all, in a very subtle way. It knew because the electron operator from the edge is either a boson or a fermion, if n is even, in exactly the same way that agrees with the Laughlin wave function. So this is the first hint that actually this edge theory knew more than the Chern-Simons theory. It started to know about the statistics of things that are making up this quantum Hall theory. Quite a subtle and interesting.
But also, Laughlin states were bulk states, right?
Absolutely. Right. And these are edge operators. So I think there's, on top of this, the assumption that whenever the object is in the bulk that's creating this, you can move that object to the edge and it should appear as.
I mean, this is an excitation localized on the edge, right?
But actually, yes, but also to take a disk of quantum Hall theory. This is gapped and is sort of incompressible. So if you were to put a hole, now a hole that carries fraction charge. Actually, let's make it simple. Let's put m holes all on top of each other. So it's the same thing as putting an electron in there. Then what happens? We even saw from the Laughlin wave function that yes, the hole is there in the bulk, but because the whole thing is incompressible, the edge sort of swells a little bit. So it's detectable at the edge because of this incompressible nature of the So yes, these are edge operators, but if you insert something in the bulk, the edge sort of knows about it. One of these gets inserted. I don't think we have any way to tell the position of the thing in the bulk. Just know it has to be somewhere at the edge. But anyway, there's this interplay between bulk and edge, which is more subtle.
But you're saying you can only decide that is you couldn't have left the bulk unchanged and just excited this on the edge.
I could have done that too, yes. But I couldn't have left the edge unchanged and excited.
That seems, there's one state, if I look at a state corresponding to an edge excitation, maybe this question isn't so well posed, but is its bulk described by the ground state or the one whole Laughlin excited state?
So there are various edge excitations. Some of them are neutral. They're the excitations without phi in the exponent, just the so they live purely on the edge. Now, then there are the charged ones. They're basically for e to the life, like this guy. These are certainly excitations that you see on the edge. But if you were to put something in the bulk, it would give exactly such a response on the edge. I think that's the right way to say it. By the way, did that answer your question? Because I didn't say the word ground state.
No, that's okay. I was just trying to ask, is it the case that if I wanted to excite something on the edge, I would have to change the bulk wave function? Or is it that for the same bulk, I have some freedom? If I had literally some degree of freedom living on the boundary,
Yes.
and some stuff in the bulk, then I can keep the bulk unchanged and either excite the degree of freedom on the boundary or not.
I think I can do that. Suppose let me put sort of an electron in the bulk,
Yeah.
and then it'll give rise to one of these operators on the edge. But now as I move it around the bulk, it still gives rise to one of these operators. And if I move that electron physically to the edge, then it clearly gives rise to something on the edge. But I think, this is my understanding, and it might be wrong, I think there's some redundancy. That the edge doesn't know everything, it doesn't know exactly what it knows. But actually, see a slight caveat to that. In the next lecture. But it's got to be something.
So putting an electron in the bulk must be taking me to one of the solitonic sectors for the phi. I mean, it must be winding mode plus Fourier. So let's say if I have...
But this is the winding.
This is winding mode, right. So there are also those things in which I just have the Fourier
Yes.
and no winding mode.
So they're definitely edge modes only with no bulk.
So what do they correspond to? There's some purely surface transport phenomena.
Yeah, I can tell you what they are from the Laughlin wave functions. It's just monomials here. So things like, so let me define Sn for Z, it's the sum over I. So they're just these somehow. So multiplied by a bunch of these correspond to the. And you can, and in fact, in the lecture notes, I compute the partition function for these modes, compute the partition function for chiral boson, and just show.
I see.
You can see that very clearly.
The stuff that comes from this abstruse identity of the theta functions.
Actually, no, it's much easier. Just count. With physics.
I mean, just to go back to something which you brought up. If it's the case that you have to change, the edge modes correspond to holomorphic excitations in T and the edge coordinate, right? The bulk wave function was holomorphic in space.
Or this is going to be the punchline of tomorrow's lecture.
Oh,
so let's because I don't understand.
Okay.
Yeah.
Okay,
we can have a long discussion on this.
just say one thing, that if you needed to excite the bulk to excite the boundary, then of course there might be some kind of physical reason why there's a map. That's what I was getting. If incompressibility meant you had to do some change in the bulk to affect the change in the boundary, or maybe you say it's enough to change that a change in the bulk affects the boundary.
I don't see how that works for this map that we're going to need to. So there's just one last thing I want to tell you, which is kind of obvious if you think about it. This was normal ordered e to the I and phi. Phi has periodicity 2 pi, so you put any integer here. The smallest operator you can write down is e to the I. Okay, what is that? Well, it should be obvious what it is. This is the quasi-null. So the quasi-null is the normal order e to the n. Okay. Can't have anything smaller than this because the compact nature of phi. So this has, you can check just using these same commutation relations. This has charge of 1 over m, as it should. And psi qp, you want to compute its statistics. Using again Baker-Campbell-Hausdorff formula. Pi over m. You get this when the phase of plus or minus now depends on the sign of sigma minus sigma. So it depends on the ordering of sigma minus sigma. So, right, so again, we see that this edge knows about the kind of excitations that one can have. It knows that it can have quasi-Nord excitation to have fractional charge and fractional statistics, and it knows what. So we start seeing this edge is a very simple theory, it's just a chiral boson, but it knows much more about the problem than you might imagine. It knows that it's made up of those on both sides, so it knows what the quasi-Nord excitations are. And where we're going in the next lecture is we're going to take this edge theory, just a chiral boson, and we're going to show that from it you can reconstruct what we started from. The edge actually knows about the Loveland wave function, and that's sort of the magic of this story. Also, we're going to do two things in the next section. We're going to show that magic, and we're going to show a beautiful experimental result that says that Ohm's law is wrong. Which is wrong.
What is that?
Ohm's law. What you learnt in school is not always correct, and we'll do this. A beautiful two-line argument, again due to Zhao Gangwei. We'll see how that works out. So it should be nice. I'll stop.